Hello class. Today we're going to practice some more Vesper theory. I have the textbook opened to page 390, question 935. In that we're asked to predict whether each of the following molecules is polar or nonpolar. So to make that prediction intelligently, you have to know how to draw the Lewis structure. Hi, Rebecca. You have to know how to do the Lewis structure. You have to know how to derive the geometry of the molecule from the Lewis structure and what Vesper theory tells us. Hi, Demi. And then from there, you have to determine whether the bonds are polar enough and whether they create a dipole within the molecule itself, because it's possible to have polar bonds but a non-polar molecule. We'll see how that plays out when we do the various examples. So the first example is carbon tetrachloride. So the problem number is 935. This is period 4 course. So day 5 of Coronachem. We're not even really doing this officially yet. The official start date is April the 6th for all this stuff. And then I guess by April 6th I'll be taking attendance. Well, you'll be checking in. That's how I'll do attendance, and I'll just keep a record of who's showing up. And then that way I can generate a mark for you, because in all fairness, if you're paying attention, you're going to learn something. If you're sitting at home playing video games, then you're not going to be learning much chemistry. But I assure you that if you come, you will get through the curriculum. I'll get you through it somehow or other. Right now we're sort of stuck in chapter 9, because that's I don't even have the notes for that, so I'm basically flying by the seat of my pants today, to be perfectly honest. But I do have all the contents of chapter 9 on my site. All right, so all Tambe. Hi, Tambe. So I have all the stuff that you need on my site. All you have to do is watch the videos. They've been recorded from like 8 years ago, since starting back as far as 2012. So everything you need is on there, including the notes on a big board. This is to sort of take you through what you should be aware of, what you need to learn. So I'm assuming now you've read through the chapter 9 that is. You know how to draw Lewis structures, and you know the names of your polyatomic ions. I'm assuming all that. So, but we're still doing a review. We haven't really hit any new material just yet. And I'm thinking of, because I'm still here with my wife in Edmonton, I'm thinking I'm going to do chapter 14 or 15, I forget which one is the one on acid-base theory first, because that'll be easier to cover. There's less note-taking involved, and it's a bit more calculations. Whereas the ones that are more note-intensive, I'll defer for later. Although, again, all the notes for that are already online. All you have to do is watch the video. So really, I could just sit here and tell you, go watch this video. But I don't like doing it that way, because students like to have their hand held a little bit, right? They like to know, okay, this is what we're doing today. This is what I should go look at today. And it gives you a better sense of control if I take you through it day by day. But spread the word, folks. I'm only getting 3 people here. I know the class has something like 30 people, so there's 27 people who are absent and who are missing out on the lesson. Go wake them up a little bit, maybe. Not right now, but after class. So, okay, carbon tetrachloride. Start by drawing the Lewis structure. Carbon always has 4 electrons, chlorine has 7, and there's 4 in the molecule, so 28 plus 4 gives you 32 electrons to account for. So draw your preliminary Lewis structure. Draw all the octets on the satellite atoms. And that's carbon tetrachloride Lewis structure. There's 4 domains, and they're all bonding. So that's going to point to a tetrahedral geometry. And the way you draw a tetrahedron is you draw 2 atoms in the plane of the board One's coming out at you, one's going behind. Bond angles are all 109.5. And because chlorine is highly electronegative compared to carbon, it's all the chlorine atoms are going to have a dipole. But because the dipoles are pointing in different directions, what's going to happen is, okay, these two have a dipole pointing this way, so the resultant for these two is pointing up. These two have a dipole pointing that way and that way, so the resultant of these two is pointing down. So you see the two resultants will cancel. And although the bonds are polar, the molecule overall is non-polar. Mama, you want to go outside? He's standing in front of the patio door. Okay, you want to go outside? There you go. The next one, sorry for the interruption. The next one is ammonia. So the molecule overall is non-polar. Bonds are polar, but symmetry cancels dipoles. So the overall molecule is non-polar. Carbon tetrachloride used to be used as a industrial solvent. It's also resistant to fire. You can throw it on fire, it'll put the fire out. But then they found out that absorbing it caused liver damage, so they quietly stopped using it. They discovered the same chloroform. A lot of chlorinated solvents are toxic to human metabolism, especially if they're absorbed in fairly large amounts. Your body tries to detoxify them, and very often it actually produces a substance that's even more toxic as it's trying to detoxify it. If you ever get a chance in university, I recommend you take a course in toxicology. It is a burgeoning subject. There are levels of toxicology that we have not appropriately explored. You know, everybody talks about toxicity in ways that makes you sick. But what if you have toxicity that just alters your fertility? You won't get sick, you just won't get pregnant. That kind of toxicity, in my opinion, is far more insidious than the toxicity we normally define as toxicity, where you feel sick, or you might feel nauseated, or some other hard to ignore symptom. So 935B now is ammonia. Always start with your Lewis structure. Five valence electrons on nitrogen because it's a part of nitrogen group. Mama was staring at me, he's making me nervous. Look at him. Mama. Yeah, sure. You gonna learn some chemistry? Yeah. Okay, 1 times 3 for the number of hydrogen atoms. Total is 8 electrons. Okay, so draw your hydrogen atoms connected to the nitrogen. That uses up 6 electrons, and then you have the last 2 on the central atom. So ammonia has 4 domains, 3 bonding domains, or you can say bonding pairs. Sometimes you'll notice sometimes I say bonding domains, sometimes I say bonding pairs, because sometimes you get double bonds. That's 1 domain. 2 bonds is 1 domain. 3 bonds, 1 domain. It means you have an area where there's electrons. That's all that means. So here you have 1, 2, 3, 4 areas where there's electrons. So I know some of you had some confusion about that, but okay, there's 4 domains here. 3 bonding pairs, 1 lone pair. That's called pyramidal. It's a tetrahedral archetype, but it's called pyramidal when you have this combination. So you're gonna draw. What I like to do is I point the lone pair up. That's not the only right way to do it. That's just the way I like to do it. And you draw your other hydrogen atoms like a tripod. So the molecule looks like a tripod. Bond angles here are about 107. And this is definitely a polar molecule because the nitrogen atom is more electronegative than the hydrogens. So the electrons get pulled this way. So the resultant dipole is pointing upwards, negative upwards, and the positive is down, opposite the lone pair. Let's do C next. C, SF4, sulfur tetrafluoride. Yeah, sulfur tetrafluoride. Okay, Mom, I hope you're happy now. The house is like -4. So sulfur has 6 electrons, fluorine has 7, and there's 4 fluorine, so 4 times 7, 28 plus 6 give you 34 electrons. 4 times 7, 28 plus 6, I said, right? 34 electrons. Draw your fluorine atoms, attach the sulfur, put the lone pairs on there. Okay, that uses up 4 times 6 is 24, 26, 28, 30, 32. 2 more have to go, put them on the central atom. All right, how many domains is that? 5, that's right. 5 domains. 1, 2, 3, 4, 5. 4 bonding pairs, 1 lone pair. That tells you what? It's a trigonal bipyramidal archetype, but when you have 4 bonding pairs, 1 lone pair, what you get is seesaw. So draw the molecule this way. 1 up, 1 down, 1 going towards you, 1 atom going behind the plane of the board, and then I guess you could draw the lone pair standing like that. So you can imagine this molecule sitting on these would be the legs. This is the board of the seesaw, and the electron pair is standing in the middle of the board, balancing. So clearly this molecule is not symmetrical. Fluorine atom is very electronegative. It is the most electronegative element on the periodic table. So these 2 dipoles will cancel because they're pointing in opposite directions. But these 2 will not. They tend to point this way and that way. The resultant will be that you have a dipole pointing that way. Okay, so the dipole of sulfur tetrafluoride is pointing away from the lone pair, and so the molecule is polar. Because of that. Xenon tetrafluoride. We didn't do this yesterday, did we? No. Okay. No, yesterday we did 921. Yeah, 935. We're doing D now. Xenon tetrafluoride. Now you got xenon and you got fluorine. Xenon has 8 valence electrons. Fluorine has 7, and there are, what am I doing? 7 times 4. So 28 plus 8 gives you 36 electrons to be accounted for in the Lewis structure of xenon tetrafluoride. Let's show what that looks like. Four times 6 is 24, 26, 28, 30, 32. 4 more electrons to disperse. They end up on the central atom. So that gives you 6 domains. 4 of them are bonding, and 2 of them are lone pairs. If you look that up on your chart, that gives you a square planar geometry. Remember, the lone pairs want to be as far apart as possible. The archetype is octahedral. When you have 6 things stuck on a central atom, you get an octahedral crystal shape, but you don't see the lone pairs because when they do X-ray crystallography, the lone pairs don't show up. So what it actually ends up looking like is square planar, but those lone pairs are still there. One's above and one's below. That's the only way they can stay 180 degrees apart. If you put them in any other configuration, they're only 90, and lone pairs do not want to be at 90 degrees to each other. So that's the only configuration you're going to see that is viable. So one lone pair goes up, one lone pair goes down, and you got 2 fluorine atoms coming out at you, and 2 of them going behind the plane of the board. And that's what square planar looks like. Oh, we didn't do the analysis of the polarity of the molecule. What do you think? Polar or nonpolar? The bonds are polar because the fluorine atom is more polar than xenon. But because of the symmetry of the molecule, all those dipoles cancel, and overall the molecule is nonpolar. You got it, Rebecca. Nonpolar. Due to symmetry. That's the thing. Symmetry will do that. You may have forces inside the molecule, but if they're equally balanced, they cancel out. All right. Methyl bromide. So there's 4 electrons on carbon, 1 on hydrogen, there's 3 hydrogens. Bromine has 7. Total is 14 electrons to account for. So draw your hydrogen atoms connecting to the carbon, and then there's a bromine on there too. This is a methylating agent. If you want to stick a methyl group on something, you use bromomethane or iodomethane or some halogenated methane. Drug dealers love that chemical because they can make things like methamphetamine. Meth means methyl. There's a methyl group right there. All right, so let's disperse the lone pairs to make a valence shell, a complete octet for bromine. That's going to use a 2, 4, 6, 8, 10, 12, 14. All the electrons are used up. You can see the central atom has 4 groups on it, 4 domains, and they're all bonding. So that's a tetrahedral geometry. And the way you would draw that is you could put 2 hydrogens in the plane of the blackboard, 1 hydrogen coming out at you, and the bromine going behind the plane of the blackboard. Clearly, that's an asymmetrical molecule. Bromine is more electronegative than carbon. Hydrogen, how does it go? What is the electronegativity series? It goes like this. Von, Col, Burr, K, H, metals. So, bromine, the hydrogen is less electronegative than the carbon, so the dipoles will be, they'll be weak to begin with, but they'll tend to point towards carbon. And then the bromine as well is pulling it that way, so the general, the resultant will be that way. Okay, so there is a resultant dipole. Bromomethane is polar. Let's do number 936. Oh, we got one more. Gallium hydride. Gallium. Oh, wait a minute. Balgaintolet's in group 13, right? That's the first one I haven't remembered off the top of my head. Yeah, it's got 3 valence electrons. So gallium has 3 valence electrons, hydrogen is 1, and 3 hydrogens. So the total is 6 valence electrons. So gallium is going to have a sestet mamau. Don't touch that. Look at him. He's brewing. He's trying to make trouble. He's going to make trouble in a minute. Watch. Look at him. He's right next to the phone. Hey, you're trying to make trouble, aren't you? Don't touch. So 6 electrons. There's 6 electrons in gallium hydride. So that's 3 domains, all bonding, and that means it's going to be a trigonal planar. And that means the bond angles here are 120. That's creating symmetry. Whether or not there's a difference in, I'm guessing that because gallium is a metal, the electronegativity is going to be pointing that way. But it doesn't matter which way the dipoles are pointing, because symmetry will cause them to cancel. That's a nonpolar molecule. Nonpolar due to symmetry. Let's do 936 together. Iodine monofluoride is almost a giveaway because it's only 2 things. The fluorine atom is clearly more electronegative than iodine, so it's going to be it's going to have a dipole. That molecule is polar. That's for 936A. Now let's look at 936B. I've never seen Mama do this. I'm lecturing and he's sitting behind the phone watching it. What are you doing?
He's your new student.
He is. Look at him with those blue eyes staring at me. You're making me nervous. 936B is carbon disulphide, CS2. So carbon has 4, sulfur has 6, and there's 2 sulfurs. So 12 plus 4 gives you 16 electrons to account for. Connect the sulfurs to the carbon. If you disperse lone pairs on the sulfur, 2, 4, 6, 8, 10, 12, 14, 16. This would, well, first of all, it won't give you a complete octet, so that's not going to work. Let's do that. We'll share these lone pairs. So we'll get carbon disulfide having double bonds between carbon and sulfur. So the result is 2 domains. 2 domains, therefore it's linear. They're all bonding. And it's linear. And it doesn't matter which way the dipoles are pointing because they cancel out due to symmetry. So the molecule is nonpolar due to symmetry. It's like similar to carbon dioxide. It's analogous to carbon dioxide. Carbon dioxide is so nonpolar, it's actually used as a solvent for extracting caffeine out of coffee. They actually use supercritical carbon dioxide. You pressurize carbon dioxide to 5 atmospheres pressure, and the carbon dioxide, they let it percolate it. They percolate it through the coffee beans, and it literally extracts the chemicals out of the coffee beans. And then that's how you get decaffeinated coffee. They don't even have to grind the coffee. They can decaffeinate the beans without grinding them. And then the carbon dioxide is easy to evaporate. All you have to do is let it repressurize to normal atmospheric pressure. The CO2 will volatilize, and then it'll leave behind whatever it extracted. In this case, the caffeine, which they can then use to put into Coke and whatever other formulations they use caffeine in. So carbon disulphide. Sulfur trioxide is the next one. That's SO3, and that would be 936 C. So 6 for the sulfur, 6 for the oxygen, on which there are 3, so 24 electrons. And if you draw the Lewis structure, it looks like this. And if you give octets to each one of the oxygen atoms, you're going to use up 6 times 3, 18, 20, 22, 24. But this will not give you, this will give you -1 charges on all the oxygens and a +3 charge on sulfur. It probably makes more sense to share those lone pairs. And then sulfur trioxide will look like this. It'll have double bonds. And that's 3 domains around sulfur. And yes, sulfur is capable of expanded octet. So 3 domains points to and if they're all bonding, points to trigonal planar geometry. So the bond angle here is 120. It's a flat molecule like a ceiling fan, based on what the Vesper theory says. Sulfur trioxide would also be nonpolar, even though it's got oxygen atoms in there that are quite electronegative. The symmetry will cause those dipoles to cancel. So I predict sulfur trioxide would be nonpolar because of that. You would be able to dissolve it in organic solvents. Mind you, it's quite reactive. It's not a super stable substance. So when you expose it to moisture, it actually combines with water in the air to form sulfuric acid. So for that reason, in fact, they used to use sulfur trioxide extraction from chimney stacks as a way of generating sulfuric acid, which is an important industrial chemical. Next one is PCl3, which is D. 936D. PCl3. So phosphorus. Right, that's good. The mic is going to pick that up.
Oh, is it?
Yeah.
So,
21 plus 5 gives you 26 electrons to account for, and there you go. So that's 3 times 6 is 18, 20, 22, 24, 26. Okay, so there's the Lewis structure for phosphorus trichloride. That's 4 domains. 3 of them bonding, 1 of them a lone pair, so that's pyramidal geometry. So it'll look like this. Put the lone pair up, just like ammonia. 1 coming in the plane of the board, 1 coming forward, and 1 going behind. Okay, so it looks like that, and the lone pair is pointing up. This is polar for sure because all of these chlorine atoms have a dipole compared to phosphorus. They pull the electrons towards themselves. And the resultant of those 3 vectors is pointing downwards. Last one is second last one, SF6. That's E. Marker's giving up the ghost here. Let's get a new one. So there's 7 electrons in fluorine, there's 6 fluorine, so 42 plus 60, 48 electrons to account for. It's going to look like this, the Lewis structure. And there's lots of electrons to draw. Take my word for it, it goes 6 times 6 is 36, plus 12 gives you 48 electrons. That's the Lewis structure, and each fluorine atom has the 6. I just don't feel like drawing all of them. You have 6 domains, you get all of them bonding, so that's going to be octahedral geometry. And the octahedral geometry is perfectly symmetrical, 1 up, 1 down, 2 coming out at you, and 2 going behind the plane of the board. So because of that symmetry, even though the fluorine atoms are more polar, more electronegative than sulfur, they pull the electrons away from the sulfur, but the forces are perfectly balanced, so all the dipoles cancel. The molecule is actually non-polar, and that means it would be soluble in some organic solvent. The last one I want to do with you is IF5, iodine pentafluoride. Iodine contains 7 valence electrons. Fluorine also contains 7, and there's 5 of them, so basically there's 42 electrons to account for in the structure. You'll draw the iodine atom as the central atom, fluorines as your satellites. Let's draw the octets on this one, because I'm not sure how it looks. I'm just flying by the seat of my pants. But we'll figure it out, and it'll prove the power of Vesper theory. So 5 times 6 gives you 30, 32, 34, 36, 38, 40, 42. There's one more lone pair on the central atom. So that is 6 domains, 5 bonding pairs, 1 lone pair. That points to a pyramidal geometry, square pyramidal. And it looks like this. You got the iodine atom in the center. I like to put the lone pair on the bottom. 1 fluorine atom going straight up. 2 of them coming out at you. And 2 of them going behind the plane of the board. Okay, and it looks like a pyramid. If you were to draw lines to that peak fluorine atom, it would be like a square-based pyramid. And this is definitely a polar molecule because the fluorine atoms are more electronegative than iodine. These ones cancel because they pull in opposite directions. So this one is opposed by that one, this one opposes that one, they cancel out. But this one doesn't cancel out, so the resultant dipole is pointing upwards. So this molecule is polar. And that's it for today, folks. Tomorrow I may start doing some of the acid-base theory. In the meantime, try to do some of these questions. Remember the 80 questions I gave you as a possibility, and also continue to practice. The more you practice, the more knowledge you'll have. The more knowledge you have, the better you'll do in the final exam if we end up having one. All right, see you soon. Bye-bye.